All right, so in this video, we're going to talk about ion formation. All right, and then there's some periodic properties that we could look at that could help us identify, or at least help us to hypothesize what type of ions a particular atom will make. All right, so this is kind of stemming off from the previous video that we looked at earlier. Now, if you look at this periodic table here, we see that pretty much the periodic table separates into three major groups. You got your metals, metalloids, and nonmetals, right? And like we talked about before, metals typically tend to lose electrons when they become an ion, or we call them cations. All right, so make sure you kind of know these words. And then your nonmetals, they typically gain electrons when they become an ion, and we typically call these anions. All right, so here are your two groups. Now, what about those type of elements that will, that kind of lends them, like what about metals that tend to lend them to lose electrons, and what about non-metals that tend to lend them to gain electrons? Well, there's two properties that we could look at, and we're going to kind of talk about that brings about this point here. So first, we're going to talk about ionization energy. All right, and let's kind of look at the definition. So ionization energy is the energy required to remove one electron from a single atom in the gaseous state. All right, and typically when we're talking about ionization energies, we're talking about removing electrons from the valence shell. So how much energy does it take to remove an electron from the valence shell? All right, and so why does it require energy? Well, when you kind of think about this, right, electrons have an attraction for the protons, right? And so if we kind of draw this here, if we have our nucleus, so this is our nucleus, and the nucleus is a positively charged nucleus, right? There you have protons and neutrons, and most of it are, the nucleus is positively charged. All right, and then so if you have your orbitals here, right? This is the Bohr's model. Here's your electron. Now, here's the valence electron, and so there is this attraction that exists between the protons and the electrons, right? Because they're oppositely charged. And so because there's attraction, so it's going to require some amount of energy, which we call ionization energy, but it requires some amount of energy to remove this electron because you have to break or overcome that force of attraction, okay? And so, as I said, we call that ionization energy, the amount of energy it takes to break that force, to overcome the force of attraction. All right. And so if you look at the periodic table, believe it or not, amongst all the other different categories and patterns that we've already discovered from this point on the periodic table, there's even more, right? And then when it comes to ionization energy, it just turns out that as you move up the periodic table, all right, you see that ionization energy increases. Okay, and so if you were to compare like cesium versus sodium, sodium will have a higher ionization energy than cesium. Okay, but then most importantly, as you move across the periodic table, you see the ionization energy also increases. All right, and so when you kind of think about the major groups and what's going on here, is that then you will see that your metals, all right, typically have low ionization energies, all right, and then your nonmetals, which are over here, will typically have high ionization energy, all right. And so this really actually explains why metals tend to lose electrons. Okay, they have very low ionization energy, so the amount of attractive force is not as strong compared to those of your nonmetals. So it just doesn't take as much force, all right, to remove an electron from a metal because they typically have low ionization energy, or they have lower attraction forces amongst its valence shell and the nucleus compared to the nonmetals. All right, so we could use ionization energy, as I'm trying to say before, to kind of explain, all right, metals lose their electrons because their ionization energies are low. The force of attraction are weaker, and because it's weaker, it's just so much easier for these metals to lose their electrons to become anions or cations. I'm sorry. So the question is, what about nonmetals? All right. What about anions? Like, what is it about anions that they're more likely, or nonmetals that more likely that they gain electrons? Well, that is answered by um, talking about electron affinity. So, what is electron affinity? So, electron affinity is the energy released on adding an electron to a single atom in its gaseous state. So, what does this mean, right? So let me kind of just draw this out to the side here. And so let's say, once again, we have our proton, right? I mean, our protons, our nucleus, which consists of protons. Nucleus overall is a positively charged, right? And then, we have our orbitals here. Okay. Here's our orbitals. Here's, this is a sloppy one. All right. So let's just say this atom here, right? It has 7 valence electrons. It only needs 1 more to become stable, to have a noble gas configuration, right? And that's why it becomes an ion. So let's say it comes in and gains this electron. Now, when it gains this electron, there's a new established force between this electron and this nucleus. When that happens, all right, energy is being released. All right, so the exact opposite happens for compared to ionization energy. So remember, when we talked about ionization energy, you need energy in order to remove an electron from the atom, or from the attractive force. Okay, while electron affinity describes the opposite phenomenon. So when an electron is added, how much energy is being released due to an electron being added, okay? All right, so that's kind of the biggest difference between ionization energy and electron affinity. So when an electron is added, energy is being released. And oftentimes that's a good thing, right? And so when we're looking at this trend, what we find here is that as you go up the periodic table, the electron affinity increases. Okay, so if you were to compare the electron affinity of xenon to neon, you see the electron affinity increases. All right. If you're comparing magnesium to barium, we could say that magnesium have a higher electron affinity than barium. But as you go to the right, which this is the more important part that we're going to talk about, we see electron affinity increases. All right. And so kind of going back to the 3 groups that we were talking about earlier, or mostly 2. So if you notice, if you look at our metals here, right, then we see that our metals have low electron affinities, while our non-metals tend to have high electron affinity. Okay. So all in all, it doesn't really make a lot of sense in the case of energy for metals to gain electrons. Okay, because if they were to gain electrons, due to the fact they have low electron affinity, they won't release much energy at all. Okay, and to some cases, none. Okay, and so from an energetics point of view, you will find that metals won't typically take in electrons because they will not release tons of energy. And oftentimes, atoms like to lose energy, right? Because they like to stay in the lowest energy state as possible. Versus if you were to compare to our nonmetals, all right, if they gain electrons, they will release a lot more energy, all right, which will make them a lot more stable. Okay, and so elements like neon, chlorine, bromine, iodine, acetine, these guys, they tend to have some of the highest electron affinity, just due to the fact that they only need 1 more electron, and when they gain that 1 more electron, and then they will release tons and tons of energy. The chemical reaction tends to be quite energetic, and so this is the reason why you will find your nonmetals in this case typically will have higher electron affinity. All right, and due to the fact they have higher electron affinity, that they release tons of energy, nonmetals tend to gain electrons because it's better for these type of substance in terms of energy. Okay, and so this is kind of the biggest difference between your metals and your non-metals. So in case, just kind of recap, your metals, all right, it's due to the low ionization energies. They have very weak attraction between the valence electrons and the nucleus, and so this is the reason why they give off their electrons fairly easily. All right, so they typically become +1, +2, +3s, +4s. I mean, some atoms can go all the way to +7. They tend to lose their electrons fairly easily because the force of attraction between the valence electrons and their nucleus are weaker, right? Ionization energies are low, right? Versus if you're non-metals, ionization energies tend to be very high. And so for the fact that the ionization energies are very high, it's just harder. It takes tons of energy to remove an electron from a non-metal. But on the flip side, the electron affinity of nonmetals are very high, meaning they will release tons of energy if they were to gain electrons. All right, and so nonmetals, when they gain electrons and release tons of energy, they become a lot more stable. All right, and so this is the reason when nonmetals take in electrons, they become anions for this reason.